Right. I hope everybody had a nice break. Welcome back. Today we'll talk about balloons. Last Friday we talked about rockets. And before I start with balloons, I want to finish off with one demonstration that comes from rockets that we didn't have a chance to do because it was loaned out. And just to remind you, and actually to answer a question that's coming here, so rockets propel themselves forward by throwing their own fuel out in one direction. And the act of pushing the fuel out in one direction causes the fuel to push back. That's the action-reaction part of rockets. It's not what happens to the fuel after it leaves, whether it hits a launch pad or hits the air, any of that. It's the act of throwing it out that propels the rocket forward. Because if you push fuel, fuel pushes back. Based on that notion, you can calculate how fast a rocket should go for a given amount of fuel you've thrown out at a given speed. And so a question comes in, what equations do I expect you to know, formula? And the answer is none of them. I mean, they're interesting, particularly for people who want to launch rockets, but the details don't matter. You won't remember them anyway 20 years from now. But you might remember that a rocket, if you and some small people might be there launching rockets for fun and games. You know, what's propelling them up there? Or you're at a 4th of July event and you're watching rockets fly off. You know, what's propelling them? They're throwing fuel down and as fast and furiously as they can. And so we have something that has fuel. And Talia, Julia, you want to come down? Okay, so I've prearranged people to do the demonstration. Yeah, you can. Whether they're, yeah. Anyhow, so what this is, it's a carbon dioxide fire extinguisher. And normally a carbon dioxide fire extinguisher is built with a diffuser on it that spreads the gas out. So the gas it's got lots of carbon dioxide in that tank under enormous pressure. We'll talk about pressure shortly. And when they, Talia, you want to go first?
Sure.
Okay. Earmuffs, just because it's loud, okay? When she squeezes the trigger, and I pull the little pin out here, your job is going to be to sit on this cart with nothing touching the ground. I mean, just have a seat, okay? And you will reach behind yourself, and you'll find the handle has two parts, right, bottom and top. There, these two. And in a minute, you'll squeeze them together briefly, and you will jet across the whatever this is, stage. So what's going to happen is the carbon dioxide under pressure is going to blow itself out. There's nothing burning here, right? It's fuel in the sense that it's being ejected fast. It's going to go out fast and furious, and I'll catch you at the far end, because okay? You know, squeeze until you get about to here and then stop. Okay, ready, get set, go. Yay! Julia, you get the return trip. There are usually about 2 trips in this. So it's the act of throwing the fuel one way. You see it coming out. The fact that it did hit the wall over there, big deal. That's the fuel's business and the wall's business. But the act of throwing the fuel out, propel it. Get your feet up. There you go. Squeeze the two together, and you can let it go until it runs out. Oops, the catcher forgot. Thanks, Julia. All right, yay. So you now have ridden a horizontal rocket. All right. Any questions about how rockets propel themselves? Yeah, okay. Do we have class the Wednesday before Thanksgiving? No. All right. Yeah, they long since, I think when I first came here we did, and that died. There will be class on Monday. You can imagine the attendance. You know, there's one. It's like Barkley. If a tree falls in the forest and no one hears it, does it make a noise? If I give a lecture and no one hears it, okay. Berkeley. Okay. So rockets. Then on to balloons. I use the word pressure in talking about the gas that's in that. And in fact, it's more complicated than that because it's there as a solid. Is that true? Yeah, no, it's actually there as a gas. But anyway, pressure is going to be an important part of today because I'm going to talk about balloons. And in doing that, we're setting aside, at least for the moment, the world of objects that we've, up until now, everything's been an object, something that you could push on, you could exert a specific force on. Things were simple in that respect. But now if I start talking about things that don't have fixed shapes, like what's inside a balloon, it doesn't have a fixed shape, some of the ways we deal with it are different in physics. And things that don't have fixed shapes, substances that don't have fixed shapes, are generically called fluids. So sometimes some of these words just come out of my mouth by accident, whether I mean them, I'll use them hopefully in context properly. But fluids include gases and liquids. Gases have no fixed shape, okay, so they fit the bill for being fluids. But furthermore, they have no fixed volume. It turns out you can play around with how big a space a certain amount of gas fills. And so the gases are the most flexible of everything. And liquids also have no fixed shape, but they do have a fixed volume. A liter of water is going to be a liter of volume, whether you pour it into a pot or a pan or hold it in a bottle. But its shape can change. Okay, so today is mostly about gases. And the obvious gas to start with is the air. So in looking at a balloon, just to have one to hold in my hand, I don't want one, okay, big. I'm obviously putting something inside this. And of course, it's hot air, yeah, right. It's air. I shouldn't joke about hot air because we're going to do hot air later. But okay, so I've trapped a whole lot of air inside there. And just for your own reference, what air is, it's a gas. And what gases are assemblies of independent particles, essentially independent. They're bouncing around through empty space. They're teeny tiny things. They're moving around through empty space, hitting one another frequently, hitting the walls frequently, and they spend most of their time on their own. So occasionally they frequently bump, but that's a small part of their existence, is bumping into each other. And surely from somewhere in your past that the constituents of air consist primarily of nitrogen molecules, which are little assemblies of two nitrogen atoms chemically bonded together. That's like pushing 80% of air. Pushing 20% of air is oxygen molecules. Again, two oxygen atoms stuck together. And the rest is assorted odds and ends, argon, neon, carbon dioxide, which, as we'll see, is an important part of modern society. We're dealing with that constituent's a problem. And an amount of water that's variable. It's often overlooked. It's omitted as though the constituents of air get down into the details like xenon and krypton before anybody mentions water. Water's there, but the constituents of air are often described only the constituents of dry air, as in no water air. The presence of water is important. We'll talk about humidity, what that means down the road. But let me say that in the air around us, something like 2% of the molecules, of the particles in there, are water molecules. They may be left off the table, but they're pretty important to us. Okay? So that's what's inside this. And what are they doing? Well, they're moving very fast, actually really fast, a couple hundred meters per second. Each one is zipping along. They smack into each other frequently. Well, if the particles, okay, they're in here, they're also in here, why aren't they just rattling, flying around the room? They're making very little progress because they hit each other all the time. So the air molecules, they're moving like crazy, but they spend so much time reversing course that they don't make much progress. We are aware that they do make progress. I mean, you observe this indirectly. For example, if you open a bottle of something fragrant, if I opened one up here, little by little you would start to smell it, right? It drifts, it's what's called diffusing. It diffuses through the air because that jittering motion, which the fragrance is doing it too, they gradually, statistically make some progress in a random direction. And you can actually measure, you can learn things about the molecules involved by watching their progress. That's a whole other territory. Anyhow, so that's what's going on inside this balloon, outside the balloon. And because the particles are frequently colliding with the walls of the balloon, both outside and inside, they exert forces. Each particle exerts forces on the balloon. If you think back to bouncing balls, if you bounce balls off, if I were here bouncing balls off the wall, they would, on average, exert some force on the wall. Bing, 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 because they're transferring momentum to it. And you transfer momentum by way of forces. So long and short of it is, rather than try to make it too complicated here in the story, is fluids, we don't think of them so much as exerting a specific force on a surface, on surfaces, I should say, because how much force they exert depends on how much surface is exposed. If a little surface with this air bouncing against it, air particles bouncing against it, will experience a little force, whereas a big surface which has more opportunity to get hit will experience a bigger force. In fact, the force will scale with area. So it makes sense to describe, to characterize the gas's situation, not by how much force it's exerting on a specific surface, but by how much force it exerts per unit of surface. So for example, how many newtons per square meter, square meter being the SI unit of the metric unit of surface. You know, it's about like, it's this by this. That's a surface is 1 square meter. So how much force, for example, does this air, which I claim it can do it, how much force is it exerting on each square meter of the wall? And the answer turns out to be about, it's a pretty close approximation, about 100,000 newtons on each square meter. To abbreviate that, or just to say it in one term, we'd say that it has a pressure. The air has a pressure of about 100,000 newtons per square meter here down in this room. So pressure is an alternative to force. Force is a specific amount of force that a person would exert on a wall or a table. A pressure is a more flexible it's a concept that applies better to fluids pushing on surfaces. They don't push in one spot, they push on the whole thing. And so we look at the force per unit of surface area. And the classic unit of force is the Newton. The classic unit of pressure is the Newton per square meter. It's even got a name. It's called a Pascal. Whether you know that or not, who cares? Okay? After Blaise Pascal. Back in those days, you could be a philosopher and a physicist at the same time. They somehow diverged. He says philosophically. Okay. So, about 100, words about 100,000 newtons per square meter. That's a big force on a square meter. That means that every square meter of that wall is experiencing a force pushed that way by the air of 100,000 newtons, which is about the weight of a school bus, okay, on every square meter. And there are a lot of square meters on the wall. That's a big force on that wall exerted by the atmosphere. Question. I'll come back and ask you a bit about make sure you've got the idea of that force. The question about how do smells work and are they all gases? The answer is they're all gases. They all have to get to your nose somehow. They could conceivably be chemicals on particles drifting, aerosols, things with little objects floating around the air. We'll talk about how objects do float around the air, why they don't literally float, I should say. We're going to look at how balloons float, and a little later, why dust particles don't descend very fast. They basically don't fall very fast. It's not a floating issue, it's a difficulty moving through air. And so we'll see that the air can carry stuff. The air itself can migrate by way of diffusion, and the particles can be carried with it by circulations of the air, movement of the air. And it's interesting in different contexts, but basically we smell the molecules that float around as gas, probably with rare exception. Liquids maybe that float around on the surfaces of particles, not so much. Okay? Pressure issues. The air here, because of this random motion, and I should point out where the motion comes from. It's thermal energy. I've talked about thermal energy bits and pieces over the past month, but now it's very important. Instead of being sort of an additional part of the story, this is a central part of the story now. The particles that are in this balloon, if we took away all their thermal energy, they would glom together into a lump and sit at the bottom of the balloon. The balloon would not be inflated like this at all. The elastic skin would just collapse it into a shriveled thing. So thermal energy is crucial in creating gases. Essentially nothing is a gas if you take away all the thermal energy. There's only one exception that I know of, and that's for quantum. It's a quantum thing you wouldn't understand. Yeah, that's a stupid statement. It has to do with quantum physics. Anyhow, the particles in this have a lot of thermal energy, enough to keep them moving in frenetic motion, and giving them the ability to develop pressure, to exert forces per surface area. And that said, the question comes up like, why isn't that destructive of everything? Is that real? Are we really being pushed on like that? And the answer is yes, and for the most part, we don't even notice it. And the reason we don't notice it has to do with sort of a lot of cancellation. For example, so this paper here, it has air on one side with all the air's pressure here, exerting a force on this side. The force, because this is maybe 1/10 of a square meter, that force is like 10,000 newtons, which, put it in units you're more familiar with, it's about 2,000 pounds pushing to your left. Why doesn't that cause trouble? Well, because there's also air over here pushing the other way, and equally hard. In fact, the two are, for this vertical orientation like this, the cancellation is perfect. There is no net force on the paper due to the air. Totally canceled. The paper, however, really is being squished inward. And that's evidently not a problem for the paper. It can tolerate that inward push. Just like if you take two sides, if I push my hands on two sides of sheet paper, I can't smash it much smaller than it is already. It compresses a little bit. We've seen that when you put a wagon on the table, there's a little bit of denting that goes on as they negotiate. Same happens with paper. That pressure shrinks the paper a little bit, but not very much, and it gets settled, and it's okay. The same with you guys. You're all under this pressure all the time. Yes, and in addition to class pressure. But there's not much effect of this. Where there will be a very noticeable effect is if you make an object that's got some decent size, and you put air, you allow the air to be on the outside of it, but you take the air away from the inside of it. If I remove the air from the inside of this balloon, now there would be this pressure acting on the outside pushing in, and you could calculate how much force there is on each square meter of surface or each square centimeter of surface, but there would be nothing pushing out. And so each patch of the balloon would experience a tremendous inward net force, and it would accelerate in and the balloon would shrink to nothing, just like that. Okay? So I can't inflate a balloon with nothing. I have to put something inside that pushes out essentially as hard as what pushes in from the outside. And they're pretty well balanced. We can go into the details there. But there's essentially no net force on the balloon skin pieces because of the same pressure pushing out as pushing in. We can make an exception to that, which is kind of fun and games here. One of the first demonstrations of just the presence of ambient pressure, the pressure in the air around us. One of the first demonstrations of that was, I guess it was in the town of Magdeburg. So these are known as Magdeburg Hemispheres. So these are two metal spheres with a ring seal between them. And I can put them together. Right now they have air inside, air outside, and everything is hunky-dory. They come apart, no problem. But I can take the air out from between them, and this is what was done at this demonstration in Magdeburg. They took the air out between the two hemispheres, and then tried to pull the hemispheres apart, I think, with a whole bunch of horses, and failed. So anybody want to come up here and be my demonstration people? I need 2 people to pull on opposite ends. Rohan and one other puller. David. Okay, so right now, air's in there. No problem. We'll take the air out. And you guys can probably just barely get these guys apart. So pull hard, but be prepared for them to snap apart if you really yank, okay? I haven't taken the air out yet. I'll take the air out. Ready? Don't pull yet. Let me take the air out. This should, the air's coming out. Am I getting a good seal? Got to get a good seal. There we go. And, okay, the air's out. Let me. Okay, you guys can try to pull them apart now. So, not very successful here because the air is still pushing in, but nothing's pushing out. There's a crushing force on this little container. Okay, now let me let the air back in and watch what happens. Thanks. Hopefully that, you can see, the air pressure is real, and it's huge. I mean, they're pulling pretty hard, unable to pull those guys apart. And that means that the force on a surface, say 12, 15 square inches, was enough to prevent them from separating the two hemispheres. What else do I have to show? I can do the reverse, which is fun too. So this is a container. We took the air out from within a sphere. How about if we take the air out from without a balloon, outside a balloon? So I'll take a balloon. Blow it up, seal it off. Nothing up my sleeve. And I'll put it in a container that allows me to take the air out from outside the balloon. And you can zoom in on this officially. If you can see over there, I hate dimming the lights, but there's the balloon sitting there, happy, expecting a long life, and we're going to murder it, okay? So I'm going to take the air out now from outside the balloon. So the air inside will still be pushing out, but nothing will be pushing in. Is this working? What have I got going on here? Why is nothing changing? Oh, there we go. Some seal wasn't sealed. This is measuring the pressure. When it gets down here, there's no pressure inside the container. So we're reducing the pressure. And actually the physics of that is we're taking out air molecules. There are fewer and fewer of them, so they're occupying the same space, but they just don't hit very often because there are not so many of them. The pressure is going down. And it's not, it's halfway to zero, 3/4 of the way to zero, and the balloon is getting bigger as it tries to balance the forces. It's trying to stay in equilibrium, but the equilibrium is shifting. It has to get bigger to maintain equilibrium. And eventually, is it going to pop or not? Oh. Yay! Success. I should have a little tear coming down my arm. All right. Sorry. Not too sorry. Okay. So you can see that gases exert pressure. They have pressure. It's a characteristic of gas. Yeah. So Serena's question is if the dome doesn't have any air inside, why doesn't the dome collapse? So this dome is really thick, heavy plastic. There are things that are capable of tolerating full vacuum inside, atmospheric pressure outside, without crushing. But this is not like, if I do the same thing to a plastic bottle, can I seal this? Well, I don't even need a vacuum pump, right? disaster, right? I was just taking air molecules out from inside it, its pressure dropped, and it just gets crushed. So in order to make something that can tolerate this, you got to make it out of really heavy material. Typically, you make it spherical or circular because then the pressure pushes, the internal forces are along the surfaces, which are hard to compress. This is why containers like this with great pressure outside, little pressure inside tend to be shaped like this. Submarines, for example. You never make a square submarine. You know, a submarine cube, squish. Bad idea. Okay, you make it with spherical because it's going to be dealing with the same issues. A lot of pressure pushing from the outside. Other questions? Okay. One of the demonstrations that I typically do is put marshmallows inside this. We don't have big marshmallows today, but marshmallows are filled with little bubbles, and when you take the air out from around them, the bubbles get bigger until they get too big and they leak. So the marshmallow goes, it jet puffs, like the brand, okay? It gets really big as you take away the air around it, and then it leaks and goes back to sort of normal size. Then when you put the air back in, it gets smashed. Maybe we'll do that another day. But point is, you can see that controlling pressure inside and outside of things can change their shape and push them around. My goal is to talk about how balloons work. And so this is a first step. This is why a balloon inflates at all. You put the gas inside and you create, the gas has pressure and it's able to support an elastic skin out at a distance like this. But really where I want to go is how do you make balloons float in air? Thank you. I need help for doing anything more than half the thing at once. Okay, so how do you make a balloon float? And there are going to be two straightforward ways to do it. One of them is to fill the balloon with something that's still air, but doesn't weigh as much. And therefore, we're going to have, that's going to lighten the balloon and allow it to float. But there's a thing I've got to talk about first. And the other possibility is to replace the air with a different gas, one that has the same pressure characteristics, but just weighs less. Add a particle for particle, and that'll be for helium balloons. So we're going to look at hot air balloons and helium balloons. To set the stage, though, for doing that, I've got to tell you two things. The first is that here on the surface of the Earth, there is air pressure, and the air pressure varies with altitude. And to look at why that is, let me start by saying, why is the air here at all? Why didn't the air just drift away from the Earth and just leave? Why did we just have bare surface of the Earth and then space? And the answer is that gravity has pulled all these little air particles to our surface and keeps them there. And so the air particles down here are packed together by the weight of the air particles above them. These air particles, which are pushing on everything, will push on surfaces by way of their pressure. They push on each other by way of pressure. And so a box of air down here can be thought of as pushing outward on everything around it, including the air above it. So the air down here is supporting the air up there, and the way I think of it is box-wise, box after box stacked on top of each other. A stack of boxes that goes up 5, 10, 20 kilometers. And if you imagine just stacking the boxes like that, if they were really cardboard boxes, the box at the bottom carries the most weight, right? It's carrying the weight of all the boxes above it, supporting the weight. And as you go up higher and higher in the stack of boxes, they have less weight overhead. And that's the case for the atmosphere. The atmosphere down here is supporting the weight of this entire column of air going up to the top of the atmosphere against the force of the pull of gravity, the usual thing of weight. And as you go higher up in the stack, the supporting becomes less and less. And with that, the pressure evolves from high pressure down here to less and less pressure as you go higher. The air just simply doesn't have as much weight overhead to support. And hopefully this is familiar to all of you when you go into the mountains or go for a drive or an airplane flight or a balloon flight, I guess. Your ears do funny things. Your ears pop, they feel funny because the pressures are changing. As you go higher, the pressure gets less. And it's often noticeable if you're moving, if you do it fast enough, you can often notice that sometimes it's even painful to have the pressure change. You're feeling the imbalance in pressure between the pressure of air trapped inside your ear structures and the air outside. You feel the ear structures being pushed around by the unbalanced pressures. So the pressure gets less, and that then asks the question of, if the air up there, say in the Blue Ridge, has less pressure than the air down here, what else is different about it? How do you make air with less pressure? In fact, I was doing the same thing here. I was making containers that are full of air, but not at the same pressure. What changes are possible that will do that? And there are two important changes that will do that. If you change the number of air particles per volume, per liter, if you like, a liter is a unit of volume. If you put twice as many air particles in that liter as were there before, you basically double the pressure. Basically is just me waffling over in the tiny details, it's not perfect, but it's very close. So if you double the air inside a container by putting in twice as many air particles, shove them in, get in there, guys, they're going to hit more often. In fact, basically twice as often they're going to hit every surface, because every square inch is going to hit twice as often because there are twice as many particles rattling around inside it. So the pressure inside the pressure of air is pretty much proportional to the concentration of the air per volume. And the classic measure of concentration per volume is what's known as density, which is the mass per volume. Figure out the mass of the air, how many kilograms per volume. And the air down here on the Earth's surface has a density, mass per volume, of about 1.25 kilograms per cubic meter. It's just one of those numbers that eventually I started to remember. So that's significant, actually. I mean, it means that you take a block of air about this big, which seems like nothing at all. It's not. It's actually got some mass to it. If you shook that, it would be like shaking a little over a kilogram of flour. It's got some substance there. All right? So if you take ordinary air sitting here at room temperature and take a cubic meter of it, it's about 1.25 kilograms, and it has the pressure that I've been referring to over and over, about 100,000 newtons per square meter, which I will just call I'll just name that atmospheric pressure. Atmospheric pressure in principle depends on your location exactly. It is the current atmospheric pressure, but it's about 100,000 newtons per square meter. If you pack twice as much mass of air inside that same box, you will double the pressure. It's just simple as that. And you can do that. You can just pack the molecules in there tighter and tighter. That's how the rocket cart basically started with carbon dioxide, which you could imagine having a balloon filled with carbon dioxide at atmospheric pressure. And you start squishing them together, packing them more tightly, or keep filling the balloon, and now you're going to have to make the balloon sturdy so that it doesn't explode. And you end up with that container that was the fire extinguisher container. It's got a very heavy wall, so it can tolerate a terrible pressure mismatch between inside and outside. And you just pack carbon dioxide molecules in there until its pressure is maybe 100 times normal atmospheric pressure. So the point is then that the pressure in a gas is essentially proportional to the density of that gas. Yeah, David? Does the weight of the air above you affect your weight? Your weight is strictly determined by your gravity's pull on you. It has nothing to do with the air around you, so it doesn't have any effect on your weight, your true weight. However, we'll see that the air around you does exert a force on you. And okay, I can do this question. Just take a break here for a second. A helium balloon has mass, and yet it doesn't fall to the floor. In fact, it goes to the ceiling. Is there any real force pushing up on the helium balloon? And in order to answer this question, of course, I have to plan ahead, which I didn't do. Is this, you know, you'd think after a break I would be more on track. I'll leave it to you to figure out what went wrong. That's okay. Oh, please start. I do want it to start. I don't want that pop up. I want you to be. All right. I think I'm ready to go. There. A helium balloon has mass, and yet it doesn't fall to the floor. Is there a real force pushing up on the helium balloon? Okay, the question? Okay, see what you think. Man, it was neck and neck for a while. Here. You deserve to get to watch the fun. Yeah, there's the famous E. Okay, the answer is yes. Up until now, and I'll stop this and I'll turn. Okay, you can have fun for a second. Up until now, I keep throwing in these things, neglecting effects due to the air or neglecting friction. Well, we stopped neglecting friction pretty recently and started like embracing it. Okay. And now we're going to have to start embracing the effects due to the air. It's real stuff. It's interesting, and it really affects. No, yeah. Oh, someone got an F. Yeah. Okay. Well, question is, what grade do you want for the semester? Oh no. Okay. I get this off of here. Okay. There is a real force. So I mean, the final answer to David's question is, the weight of the air above us does affect us. It doesn't literally affect our weight, but it actually lightens us when we stand on a scale. The scale doesn't read our full weight because we're experiencing an upward force. The same upward force that affects the helium balloon, it doesn't cause us to float. I mean, Willy Wonka, whatever, Charlie goes floating, but fizzy lifting gas or something. It doesn't cause us to float, but it does actually reduce our weight slightly, our measured weight slightly. Is that okay? Rohan? Is that upward force the same as the buoyant force? It is the buoyant force. Yes, exactly that. Where I'm trying to go, meandering toward, is the buoyant force. And here's the story. The buoyant force is a new force. It's a familiar, important force. It's not like the force between two electric charges and stuff, which the physicists would go all crazy over. It's an effect that's present in any fluid that develops a gradient, and in this case, it's developing a gradient in pressure, and it's developing a gradient in pressure due to gravity. So that's where I have to go with us. I've told you so far. So that's my destination for the next 5 minutes. That the air down here has a higher pressure than the air up in the mountains, and that's because the weight overhead is less, and so the squishing effect of the weight is less. And so the air down here is packed more tightly. It's denser down here than it is up in the mountains. By going to the mountains, the number of air particles in the same volume as before is smaller, therefore the pressure is smaller. They hit less often. It's okay so far? That smooth variation in pressure due to this stacking effect of air is called a pressure gradient. Gradients are to show up in physics and physical systems and in nature pretty often. And in this case, there's a pressure gradient downward it's a continuous change in pressure from low up there to high down here, that swoop. And that means that this balloon even is experiencing different pressures. So if you remember way back early in the class, I held my paper like this and said that the two forces balance. If I do this, they don't quite balance so perfectly because the pressure down here is a little higher than the pressure up there. It's more extreme for this poor balloon. The pressure down here is measurably higher than the pressure up there. I know it's only a little change, but it's there. The pressure change is there. And because the air down here is supporting the weight of the air above it. This air up here, not so much weight overhead. That unevenness of pressure leads to a net force due to pressure alone on the balloon. And that force is upward. It's pressure pushing up on the bottom of the balloon is a little stronger than the pressure pushing down the top of the balloon. They don't cancel perfectly. There's a little left over, upward. It's called the buoyant force. This is Rohan was asking about. And that buoyant force is real, and that is the force that when I said, is there an upward force pushing up on the helium balloon? Yep, that's the force. And in the case of this balloon, it's acting there, but it's not enough to support the balloon's weight. The balloon weighs more than the buoyant force is. But we can make balloons that weigh less than the buoyant force on them, and they will float. Is that okay? I can show you the buoyant force more direct. I shouldn't say. I'll show you the buoyant force, but also show you how much it is. The question then arises, well, so how strong is the buoyant force on this balloon? There is an upward force due to this crazy pressure imbalance, but how would you figure it out? And this is where it comes down to Archimedes. Archimedes figured this out 2,000 plus years ago. He realized, and let me go through I did this in a lecture video, which I posted late yesterday. Let me walk you through it, so hopefully you can follow this. That if I look at this balloon, it's being pushed on by the air around it, which ultimately doesn't quite cancel and gives a little bit of an upward push. To figure out how much that force is, let me take the balloon away and still visualize a balloon-shaped blob of air. So even though I removed the balloon, there's still an object here. It happens to be made of pure, ordinary air, and it's not falling. It's hovering perfectly. Net force 0. Well, if this balloon-shaped object is hovering here with net force 0, that means that its weight downward and the buoyant force upward on it must balance perfectly. So we know what the buoyant force upward on this balloon-shaped blob is. It's the weight of the air, the balloon-shaped portion of air. That's the buoyant force, although it's aimed upward. And the buoyant force is exerted by the surrounding air outside my blob, my hypothetical blob. So if I take the blob away and shove a balloon in there, the surrounding air doesn't notice. It doesn't care what it's pushing on. It's pushing on this, it'll push the same. So ultimately, the upward force on this balloon is equal to the weight of the balloon-shaped blob of air, but upward. And that's Archimedes' principle, that the buoyant force on this object is equal to the weight of the air or the fluid it pushes out of the way. It displaces is the official name, the official language. Is that okay? It's a miraculous realization, a stunning realization that the buoyant force is that simple. It's just the weight of the air that you're pushing away. And I can show it to you with this demonstration. I won't use air because air is too fluffy and we won't get much action. The buoyant force is too dinky to measure. But what I've got here is a chunk of metal, this blue piece of metal. And right now it's hanging with other things on this scale. And the weight, according to the scale, we know how scales measure it. It's all at equilibrium. Everything's good. Is 13 units. 13 newtons it happens to be. So the claim is if we begin to displace a fluid like water, there'll be an upward force on this equal to the weight of the displaced water. So let me displace, this is full of water, let me put the metal cylinder into the water and displace one metal cylinder's worth of water and summon up a buoyant force upward as a result. You can follow that idea? Okay? So here you go. I'm displacing the water. I'll support this guy. And so now we're pushing, I want to push a little short, top it off. Okay, we're displacing some water now. And whoa, the scale doesn't have to push as hard, pull as hard. We're down to 9.5. So we went from 13 to 9.5. That's 3.5 units that are being supported by the buoyant force now and not by the scale. So is that really the weight of the water we displaced, 3.5 units? Well, we can figure that out because this cylinder is hollow. It's a bucket. And it's the same volume as the metal. So if I put in water into this, I will put in the weight of the water displaced. This displaced the same amount of water as I will put into the bucket. All right? So I'll add back in the weight that is being supported by the buoyant force. So here it goes. In goes the water. and we're back to 13. So displacing the water really did lighten the burden on the scale by 3.5 units, which is the weight of the water that we pushed out of the way. Hopefully pretty convincing enough. Okay? So the buoyant force is real. It's easily determined by the volume of the space. So that now sets the stage, let me just get this out there, sets the stage for making balloons that weigh less than the buoyant force. How do you do that? My balloon here weighs too much. Why does it weigh so much? Two reasons. One is the air inside is not really quite ordinary air. It's been packed a little extra tightly. And the reason it's got to be packed extra tightly is because it needs to support the stretchy skin of the balloon. So the balloon is compressing that air a little bit to higher density. So the air's density inside the balloon is a little higher than it's supposed to be. As a result, it weighs, the weight of the blob of air inside the balloon weighs a little more than my hypothetical blob of air. It's packed more tightly. The other thing is the balloon skin weighs a lot. So between the two of them, we got a sinker. The net force on this is not its weight anymore. It's really, the upward buoyant force on this is significant. It will not fall at 9.8 meters per second. It's significantly slowed because the net force on it is way less than its full weight. Okay? But we can make the balloon, we can fill the balloon with lighter stuff. And one of the ways to fill it with lighter stuff, and I guess this is where I'll finish up with, is if we can change the pressure of air by doing more than just changing its density. Yeah, if we pack more air into the same space, the pressure goes up. Pack less, the pressure goes down. We can also change the temperature of the air. If we heat up the air, the thermal energy that every particle has on average increases. It hits harder, it hits more often. And so increasing the temperature of a gas while doing nothing else about it, same density, increases its pressure. And this is why you don't throw things in the fire that are sealed, sealed containers in the fire. They heat up, the pressure builds up because the particles inside are rattling around faster and faster and hitting harder, and you can burst things in a fire. So what I'm going to do is I'm going to put air inside of a balloon that is such that the air inside the balloon is at atmospheric pressure, or very close. So a lot like this. But this is too heavy. I need to make lighter air. How am I going to make lighter air that has atmospheric pressure? And the answer is, I'm going to crank up its temperature. So it'll be hotter air, and every particle will be doing more to contribute to pressure than the colder air's particles. I don't need as many. So I can fill a balloon with less molecules, and therefore less weight, while still having atmospheric pressure. You okay with that idea? So here it is. So it's just a bag. I'm going to trap that heated air inside a plastic bag. And so this is the hair dryer. If you happen to have a metal bristle hair, this is a great hair dryer for you. It's super hot. It melts your hair. But we're going to put nice hot air into the balloon. And the result of this is it's going to have atmospheric pressure inside the balloon, but there are going to be fewer air molecules, each one doing a better job of creating pressure because they're hotter air molecules. And lift off. Woo! Okay, so that volume of ordinary air would weigh a lot. But it's lighter gas because it's been heated. We might only have 2/3 as many air particles in there as before, and its weight is down by a factor of 1/3. That's enough for the buoyant force to overwhelm the weight and send it up. All right. With that, then I'll stop for the day and I'll finish up on balloons on Friday.